Hello, everybody, and welcome to Wow 11. I am Paige Hattie, the director of Mobius Connect, and I am so happy that you were able to join us for today's session. We've got a good one in store for you. So welcome to the tie between reliability, maintenance, energy, and emissions, presented by the great Howard Penrose. So if anybody has any questions for Howard throughout today's presentation, feel free to drop them in the Q&A panel on your webinar screen. And if we have some time at the end of today's session, Howard will be more than happy to answer your questions for you. So that being said, I'm going to bring on the man of the hour, Mr. Penrose. How's it going? Good.
There we go.
Good. There we are.
Yeah. Attempting a new system in the middle of nowhere, Ohio. Some hotel. Got it.
Gotta love it. I hope Ohio works with us. All right. Yeah. So without further ado, I'm going to hand things off to you, Howard, and we'll get your screen up here, and you're good to rock and roll.
Yep. And the funny part is the connection we're using is better than the hotel connection. So bear with us, folks. In any case, yes. So we're gonna talk a little bit about actually what my dissertation was back in the late 1990s, which is the relationship of energy and environment to reliability and maintenance. Just real quick, my background, ta-da, done. Let's go ahead and we'll have some fun from there. And I'm assuming that I'm up because I can't see it.
Yes, okay, your presentation's rolling just fine, Howard. Everything's hanging in for right now.
Yeah. Well, got to get used to a new system, right?
I know.
Yeah. So in the 1990s, there was a big push called the U.S. Department of Energy Challenge programs, and those were echoed through different programs worldwide. And all of the programs found that while there were some significant benefits to some of the energy efficient equipment modifications, like going from standard efficient to premium efficient motors, the largest single impact on reliability and maintenance and actual maintenance costs and energy savings in particular was the implementation of maintenance programs. So we'll skip forward to 2003. And what we found in a study called the Motor Diagnostic and Motor Health Study found that less than 3% viewed energy as a reliability metric. And then we echoed that again, that same study, same population of people, and this was a global study. 2013, we found that 0% viewed energy as a reliability metric. And in 2022, we found the exact same result. But when you think about it, wouldn't a more efficient system be more reliable? And that was one of the things we found even in the 1990s. So this is nothing new. It's just not being followed. And I've been asked once in a while why my programs survive, everything from the program we implemented at General Motors to you name it. And that was because we always tied it to energy. Unlike things like safety and other things, this is a real measurable amount. And what we did find at DOE was a minimum of 14% improvement in energy costs just by implementing a maintenance program. What we found after was places like at the National Institutes of Health, we were seeing improvements of up to 50% of the energy costs. Now today, with companies having ESG goals as well, emissions reductions and the like, there is a direct tie between that energy and the emissions. Now we're going to only focus on electrical signature analysis related stuff today, but because it's going to be easier, but everything from steam programs, other mechanical programs, we'll talk about alignment and belt tension and things like that today, but all of that has a direct impact. Tightening connections, I squared R losses, I squared R equals watts and kilowatts. So all of this has a direct impact on our energy consumption. So let's start out and we'll just look at some of what we looked at back then. So this is a from a presentation I did in 1997 um, in a repair versus replace of electric motors. So we looked at a 50 horsepower. This was actually in a power plant. The time a standard efficient motor in this size was about 90% efficient. Premium efficient motor was 95% efficient. If I look at the difference of that, which is the horsepower, so full power times 0.746, which gives me kilowatts, times the difference between the premium and energy efficient motors, that would be a reduction at full load of 2.2 kilowatts. If I look at that at demand, which if you look at your bill, you'll see a demand cost and it'll be related to kilowatts. If I have $14 per kilowatt demand, I multiply that by 2.2 times the 12 months, and that's $370. So demand is usually the maximum kilowatts you draw in a 15-minute period, which is pretty standard with utilities. The charge related to that would be 2.2 kilowatts times, in this case, 7 cents per kilowatt hours times 8,000 hours of operation, which is almost full time. There's 8,760 hours in a year. That would be $1,232. Total would be $1,600. I would look at that and say, okay, if we're looking at 8,000 hours, that 2.2 kilowatts times 8,000 hours is 17,600 kilowatt hours. Now, I could change that to pounds of CO2 pretty readily, but the number would be massive. So what I usually like to present is tons, because it sounds bigger for one thing, but the number looks more realistic from the standpoint of when you're looking. So that would be on average in the United States 0.707 tons, metric tons, which is 22,000, or I'm sorry, 2,260 something, or 2,240 pounds per metric ton. So it's 0.707 times 17.6 megawatt hours. So it'd be 17,600 kilowatt hours divided by 1,000. And that gives me 12.4 tons of CO2 decreased by going to a premium efficient piece of equipment. Now, if I repaired it, one of the things we found through the DOE, actually was the Canadian Electrical Association studies in the 1990s, was about an average of a 0.5% reduction per repair of an electric motor, of a standard efficient electric motor. We did find out later at Hydro-Quebec with the newer core steels for energy and premium efficient motors that didn't have as big an effect, but we'll use that for this example. Say a bearing wasn't installed right, or something's a little tight. That would also account for 0.5% reduction in efficiency. So if we do that, that's 0.23 kilowatts. And then we run through the same formulas, and we come up with $167 reduction, increase in energy cost after following a repair, and 1.3 tons of CO2 increase per year. So when I take a look at it, all of our decisions directly affect energy and emissions. Well, two things. One is energy is directly tied to the P&L in the boardroom. So you've got C-level interest in energy costs. The studies we're doing right now in a bunch of facilities, I'll cover a few of my case studies. We'd have to tie those energy costs related to efficiency improvements to things for the board. And then also emissions, which carries more weight because most companies have 0% by such and such a date and so on. Well, the reliability program or maintenance program can have a direct impact on that. Well, let's take a look at something more massive, because we did find that compressed air is the least efficient system you'll have in a plant. On average, it's 14% efficient. That means for every horsepower of compressed air you need 9 horsepower. So it's the least efficient system. We always recommended going away from compressed air, looking for compressed air leaks and the like. Well, you can find your estimated total losses from air leaks by looking at the pressure being put into the system and the least pressure in the system where it's not being deliberately reduced, but where it's supposed to be consistent. So this is from an actual plant in central Illinois. What we found was a 45 psi drop. I'm sorry, it went from 100 psi to 45 psi. That would be a 55 psi drop. That was due to numerous air leaks. A lot of them were silent, meaning you needed ultrasound to hear it. So we took power measurements up front using an ESA device, and you take that times 0.5% times the pressure drop. The 0.5% was a value determined by Oak Ridge National Labs. So that's from a Department of Energy study. So 220 kilowatts was measured times 0.5 times 55 psi drop. That would be 60.5 kilowatts of just feeding air leaks. That comes out, if I use that, $14 per kilowatt and 7 cents per kilowatt hour, and 8,000 hours of consistent use. Now, mind you, there's some variability, but this was always considered conservative. That would be $380 in just energy, $10,164 in demand charges, which is a significant amount. That's $44,000 just feeding air leaks in the system. And emissions comes out to 484 megawatt hours times 0.707, or 342 tons. Now, mind you, at the time we did this study, that value was 0.909 average in the United States. It's slowly coming down. In places like California, it's actually about 0.3 right now. Where I'm located in Ohio right now, it's 0.5. In Illinois, it's low. In other areas of the states, it's much higher. Now, if we take a look at another electric motor-driven system, just a belted fan application, I can take a look at belt tensioning. Belt tensioning has a direct impact. The number one thing that we always find is that belts are over-tensioned, not under-tensioned. Why? Because with turbulence, things flap a little bit at the bottom. So as a result, you go, oh, that flapping must mean it's loose, tighten it up some more. Or worse, people follow the belt tensioning tables. The belt tensioning tables are the maximum the belt can stand, but not the application. For that, you need to go to a calculator, usually available on the different belt websites, and that allows you to calculate what your actual tension is supposed to be. I had one at an automotive plant recently where we went up and they said, oh, the belts are too loose because they're flapping, and we took a look at it, and they were exactly where they were supposed to be. But we saw the turbulence. Now, turbulence has a direct impact. Best way to solve that was it was on a VFD already. We had them slow it down a little bit. They actually had more airflow and less turbulence, less belt flapping. They were increasing speed, trying to get airflow, but restrictions in the ventilation system were actually causing less airflow and greater turbulence. So it was fighting itself. And as a direct result, they were using more energy, producing less and less and less. So just by slowing it down, all of a sudden, they improved it. Now, belts and belted applications have a significant impact because what we end up measuring is all the losses that are going into components, whether that's the belt, the shev, or the bearings in the system. And that kilowatts, that's direct energy going into places it's not supposed to, driving failure, increasing heat, and decreasing life. So kilowatts is a direct conversion, right? So in this case, first off, we figure out what the frequencies are that we're interested in. This formula here, if you've watched my presentations, I use this actually relatively often. This was actually, by the way, a real case. So we take a look at it, 3.79. And then you can see here's the frequencies from that application. There's some bearing peaks, there's some belt peaks. some misalignment peaks, and then some other bearing peaks. And then, of course, if I've overtensioned the belts, I get static eccentricity. For those involved in vibration, static eccentricity results in something called unbalanced magnetic pull. So that unbalanced magnetic pull is also an energy loss. That comes out to, pardon me, sorry about that, 23 kilowatts from the belt and sheave, from a slight overtension, the static eccentricity or the unbalanced magnetic pull, which means that it's trying to pull towards the side, 0.29 kilowatts. But that unbalanced magnetic pull is also hitting the friction in the bearings, increasing those losses to 8 kilowatts. So I've got a total loss in this case on a machine of 31.3 kilowatts. That's excluding anything else. And that comes out to, using that same 8,000 hours, 274,000 kilowatt hours a year, or 194 tons of CO2. Now, if I take a look at 274, let me whip out my calculator here because I didn't put it down there, and I do not trust myself with math when I'm doing this. Let's say it's, or we can just say it's 10 cents per kilowatt hour to include demand. So that would be $27,418 per year, just because I didn't tension the belts right. And what's the cost of an average belt tensioning kit, including those little ultrasonic tensioning devices? Well, $400 or $500. So I can spend $400 or $500 in a couple hours of quick training and have somebody install a belt correctly and save $24,000 a year. That's just on one machine. How true is that? I see it all the time. So let's take a look at electric motor systems in particular. So we have in an electric motor system, incoming power, controls, motor, coupling, load, and process. We won't do anything further upstream, but we will count downstream. This is what you would see with electrical signature analysis all at once. That's one of the reasons I like it. And electric signature analysis looks at current, looks at voltage, looks at power quality. By definition, in order to do electrical signature analysis, you're using a power analyzer in any case. Now, current is always downstream, voltage is upstream. So when we're taking a look at things, we're able to separate out whether I'm looking at that machine or a different machine on the system. Now, the technology was developed by Oak Ridge National Labs and patented in 1988. So it's not brand new. And it was originally designed not to look at rotors, but to look at the complete system, in particular motor operated valves, bearings, and gears. And as a matter of fact, in the original patent, they mentioned rotor once in one sentence, that it would happen to test that. They talk about belts and fans and pumps and everything else, gears, you name it, all the stuff we've been talking about recently. So the original purpose was that. We lost sight of it over a few years and focused on just rotors for some reason. Well, those of us actually doing the technology understood it went beyond it. So I entered into this realm in 1996, studying these. 1997, I had my first electrical signature analyzer. So the other thing is speed, because when I'm going out to do something like that, I get to enjoy most of my time in motor control centers, doing multiple machines without crawling over the machines. Now, mind you, I do like looking at the machines. So when I go out and get nameplate information, that gives me a chance to do a visual as well, because you never leave out the visual. Welcome to the world of IoT devices, right? Where we stopped doing one of the most important parts, which is the visual inspection. So if I take a look at a system, in this case, say a 300 horsepower motor, and this is with electrical signature analysis. And here's my basic data. I've got input power of 193.5 kilowatts, output of 180 kilowatts. Everything in between are losses. That means at 81% load, the motor's operating at 95% efficient. Pretty straightforward. Input, output, efficiency in between. So let's get back to a plant. I'm sorry, that particular machine. 6 hours, from now on, I'm going to use 6,000 hours. So 6,000 hours per year under a constant load at $10 per kilowatt demand and 10 cents per kilowatt hour. The reason why I'm using those is because doing math while you're presenting is really bad. In any case, we'll go ahead and do that. So that particular machine, 181 kilowatts times $10 times 12 months, if it's under as the load was measured, that's $21,720 in demand. 181 kilowatts times 10 cents times 6,000, that's $108,000 for usage. The total cost is about $130,000 per year in electrical consumption just for operating the machine. So if I take a look at that as well, and I come up with my megawatt hours, which would be 1,086, that means that motor operating, just the one motor, is 768 tons of CO2 per year. So as we're able to make that application, let alone the machine, more efficient, we can reduce those numbers and get ourselves closer to what the company wants, right? Now, if I take a plant, and this is the plant we're going to use over for the next case studies, 3 megawatt plant. This is a real plant, actually not far from where I'm sitting right now. 3 megawatts, 24/7, 365, which is 8,760 hours. They take a few bits here and there downtime, but the measurements we did over 2 years showed it was right around 3 megawatts pretty constantly. So 365 days, 24 hours, that's 26,280 megawatt hours per year for that plant. The emissions would come out to 18,580 tons, metric tons, which is 2,240 pounds of CO2 per ton. The improvements, energy upgrades, that's one of the things they were already doing, commitments to purchasing green power in order to reduce their emissions, because the emissions we're using, this tons of CO2, go all the way back to the energy mix being provided. So if it's all coal-fired plants, that's 0.9. If it's all clean energy, it's about 0.2, because there's always a mix of other things in there. So the big one that they had not really paid attention to up to date was maintenance improvements. Now, they made small changes and they got excited when they saw 1 or 2% improvement. We did a study there, so we're going to cover this part, and then we're going to cover power, just taking care of harmonics and things like that. Something that we talk about, but we never do, and it always seems to affect the bearings. And what we do is, instead of correcting the problem, we put Band-Aids like shaft brushes on the machines. So let's take a look at the maintenance impact. And just to put something else there, if you have only access to a torque value, RPM times torque divided by 52 gives you horsepower. Kilowatts is horsepower times 0.746 kilowatts. Now, some of them I'll show you that we took foot-pounds of torque and converted. Now, the good news, thank goodness for the internet, and by the way, don't use the ChatGPT yet. It still has some math errors in it, we've discovered. But in any case, if you go on and just search calculators, you can change Newton meters to kilowatts, things like that. So here's a typical application. This, again, is a belted application with a fan and a turbulence. So in ESA, this is turbulence. Turbulence piles up around my line frequency. So that leaves everything else wide open. Now, if I'm doing vibration, turbulence ends up elsewhere, like around my blades or around blade frequencies, around my RPM frequencies. That's one of the benefits of ESA, is it pulls it away from that. It does mask a few things down here, but usually those peaks right on top. of the turbulence in any case. So it'll be there, but it'll be buried a little bit. So let's take a look at ESA in foot-pounds. So here's an example. These are the peaks. So if I take 5 foot-pounds at 660 RPM, going back to the torque formula, that would be 660 times 5 foot-pounds divided by 5252, or 0.63 horsepower, or 0.47 kilowatts. And then on the other one, turbulence at 48 foot-pounds. I'm just taking the one peak instead of both peaks. Technically, I should take both peaks. At 90 RPM equivalent, that comes out to 90 times 48 divided by 52, or 0.82, or 0.61 kilowatts. So this is relatively small value, thank goodness, so it appears. But if I take that, just a little bit of belt wear, that's really what it is, just a tiny bit of belt wear. 0.47 kilowatts times $10, $56 a year in demand, times 6,000 hours times 10 cents per kilowatt hour, 200. So about $338 for the belt loss. So I can make a decision whether I continue using that belt or do something with it then. Turbulence. The turbulence, on the other hand, has a $439 value. I could then take a look and see, is there an adjustment I need to make or something else in order to make improvements? What will that improvement do? Well, it'll increase the life of the belt as well. So I can stave off belt wear by correcting the turbulence issue, or I can correct it all at once, depending on if it's cost effective. In the meantime, that's about 1.8, let's just say just over 1 kilowatt times 6,000. That's 6 megawatt hours, or about just over 4 tons of CO2 per year. So at that point, I can make a decision. Is it worth it to address this? Or are there other things that I can address first? Because this is going to still last a little bit. Or I can go in our particular ESA device, we actually calculate everything out. There's the values right there. I just look at the peaks. The newest version of our system actually puts the lines up on it and takes the measurements for you, but that's neither here nor there. You can take a look at straight kilowatts. Now, if you don't have this and you just have a power meter, use the power meter before and after. Your biggest opportunities, including things like bearing wear, bearing greasing, that's a big one. Things like that are all going to be measurable values before and after, as long as you keep the load the same. So the emission opportunity for that one, 0.707, yeah, there it is, 4.6 tons of CO2 per hour, closer to 5, sorry. Math in my head, not a good thing. Okay, so let's take a look at a belted application with misalignment and belt slip. Again, this is a real application at that facility. So we take a look at it. We do have a resonance, so there's a 2-time belt frequency and a small 3-time. We call these two out. Those we can find as kilowatts. But when I start taking a look at values of this, it'll be significant. So 150 horsepower machine, 109 kilowatts in, 100 kilowatts out, which gives me a motor efficiency of about 94%. That's actually better than the belt efficiency. So let's take a look. We have 11.5% belt slip, so belt's worn, and a little bit of tension. So belt slip comes out to 4.6 kilowatts, or 552 demand, usage 3,312. The misalignment at 23 foot-pounds at 16 hertz, using those other formulas, that comes out to $2,232 total, or $5,500 just by fixing the belts and belt alignment. So when I do install equipment, precision belt applications very, very important. As a matter of fact, I like using belts because the numbers are bigger, but it's not much different than what I'll see in misalignment. So if I do just a basic alignment, I have reduced the bearing life by 60% and increased my energy consumption by a measurable amount. If I go with precision alignment using proper laser alignment, eliminating soft foot, making sure everything is correct, making sure I'm not bolt bound, things like that, taking to effect growth and everything else, I can have a measurable impact that will pay for the time to do that, and often will provide me a month or two simple payback on the alignment systems. So, and let alone training. So the impact is huge. I use ESA all the time just to do my measurements before and after whatever I'm doing. And that provides me some opportunity. So just doing just that one machine, 150 horsepower machine, belted fan, we're talking about doing proper tensioning and alignment of 32.7 tons of CO2. Good news behind that, by the way, the belt wasn't worn. It was just misaligned and not tensioned properly. So they were able to recover it. The actual application dropped it. Now, you won't get all 32.7 tons because there'll still be some friction losses in there, maybe a little bit of slip. So figured that dropped down to about 28 tons, reduced at 28 tons. So in a gearbox application, if I look just at bearing issues, and we look at a lot of gearboxes, when I start taking a look at all the improper oiling, not taking care of the oil in a gearbox, things like that, you start to see the losses show up in the bearings and gear meshing. But if we just go with just the bearings, such as in this case, when I go through and I calculate everything out, in this case here, we're doing the foot pounds and speed and everything else. That comes out to 4.25 kilowatts just from not properly lubricating the gearbox, meaning not changing out the oil when you're supposed to. That has a direct impact of 24.3 tons of CO2. Now, if I take this back to the original site, just changing the oil in just that gearbox, and it wasn't really a large one, would be about 0.13% of the total annual emissions for that plant. Now we take a look at a grosser one. This is one where we had a 10 D belts on a pulley, and we brought in a belt manufacturer, and they brought it down to 2 modern V belts, and just slightly larger pulleys. So we had to make some other modifications. But this is an actual application that reduced the total load. By the way, the output was exactly the same, from 74% to 68.9% load on the motor. So it had a just over 5% drop in load. And this is the same machine. We saw the output 161.1 down to 148, 175 kilowatts to 163 kilowatts. So when we take a look at it, I'll go on with the output because we had some bearing issues that weren't addressed. So we'll go off that. So before was 161.5, after was 149 kilowatts in the load. That is a significant drop. That's 12.5 kilowatts. So by doing that, we reduced the damage occurring to bearings. They were actually breaking shafts on this application because the pulley weighed more than the motor. Now going down to the smaller pulley, they got more life out of the machine. As a matter of fact, going from a failure every 6 months, that was 2 years ago, and they haven't failed since. As a matter of fact, it seems to be running like a champ, while also reducing energy costs by $9,000 for that application. And 53 tons of CO2 per year, which is a 0.3% of the annual. Now we'll take a look. This is not the same location. This is actually out at National Institutes of Health, 600 horsepower machine. These are the bearings. They had two 6322s on this machine here. This is actually an alignment issue. So 600 horsepower, taking a look at it, lightly loaded. We're talking about 126 kilowatts input, 114 output, giving me 93.4% efficient, which is really low, but they're at 27% load. We took the measurement. When we do the analysis, we see blade signatures. We're seeing some other stuff. Going back to our kilowatts for that, we see some significant blade frequencies, as well as bearing cage, the bearing ball, and then the outer race. The inner race didn't show a significant peak, but those add up. Pump blade, turns out that we were showing these blade frequencies because there was a ding on the blade. When they were putting it together, they had to shave down the blade in order to get better efficiency point. And somewhere along the way, they dinged one of the blades on the impeller. And that is the resulting loss. It was more significant than the failing bearings. So the total losses in the impeller and blade pass were 4.22 kilowatts, or 4.25 kilowatts on that machine, because of a ding on the blade. That was it. Maybe some other stuff, but primarily it was the ding on the blade. And then the bearings, which were failing because they weren't lubricated properly, was 1.27. That came out to $5,500 per year for that little ding. Instead of correcting it, they left it. And 34 tons of CO2 per year. So if we take a look at the total for this application, belt and turbulence for the first one, 4.6 tons and 700. So when we start totaling it all up, we're looking at $24,700 and 149 tons, basically metric tons of CO2, and that's just from 5 applications. I'll let that sink in for a second. Just 5 machines in the plant reduced the total emissions by 1% and significantly dropped the cost. Now, for the same plant, let's take a look at an overall application, reduction of harmonics in the system. Areas for energy improvement first: precision alignment. Misalignment, softfoot have a very definitive energy impact. Proper lubrication has a huge impact. Cleaning, balancing, and doing filters also has a huge impact. Belted applications, including going from really old, like big D belt applications to more modern, more energy efficient belt applications, all have an impact on the reliability of the machine and energy costs. All the load improvements, air leaks, chiller tubes, et cetera. I mean, the 50% reduction in energy we had at NIH was primarily cleaning chiller tubes. And then US DOE, they say 14%. Be perfectly blunt, 14% is a minimum. We're normally seeing much, much higher. The amount of waste we have from not properly maintaining machines is incredible. So if we take a look at that application for that facility and just implementing a basic maintenance program against their existing energy consumption, we're talking about reducing their total emissions by 1,840 metric tons of CO2 per year, and close to $300,000 per year in energy consumption. So what could you do with $300,000 with your maintenance program? I could think of a few things. Now we take a look. This is that plant. We were doing measuring at the utility meter. We just now concluded that project. This is not unusual. As a matter of fact, most of the waveforms we're looking at right now don't even look this pretty. They look much, much uglier. We're putting a lot of stuff on the grid that we had not been placing there before. So yeah, the harmonics are generally pretty high. If we address those harmonics, we'll get past that. We took a look there. They had a lot of grounding issues. They were going through bearings relatively quickly. They had neutral, unbalanced neutral circuits and a lot of neutral harmonics. We estimated, by the way, the end result wasn't 7%, it was 14%, 14.5%. But if we just look at a 4% reduction in energy as a direct result of getting rid of the harmonics. Oh, by the way, let me go back to that. That was, by putting in harmonic filters, because they had already put in power factor correction. The power factor correction, when I have high harmonic condition, actually generates more energy consumption, not less. So when we started eliminating harmonics, just started with the ground and neutral filters, we took a total reduction 3 times the values I've got right there. So we're talking about came out to close to just under, that would have been just around $500,000 per year, $500,000 per year, and the emission reductions were much, much higher. So if we take a look at that, and I use the totals I have there, then we take a look at 14% improvement. We take a look at everything else. The total percent reduction in energy for implementing a maintenance program at that facility was guesstimated $420,000 per year. The end result was much, much higher. So it's always conservative. Now let's take a quick look, because I mentioned bearings, and then we should have time for questions. I'll go really fast because I've used this case study before. I just want to show, because this is one where I had perfect measurements before, exact load, perfect measurements, exact load after, and we split the bearing that was the problem. So we have before and after measurements. This is a wind turbine. I've been doing a lot of those lately again. The plan, as a matter of fact, we have some DOE programs going on as a direct result of that. But we took the data before. This was done by a repair shop. They were out in the field. The little red markers down here are indicators of the bearing. There were some frequencies associated with the high-speed gearbox thrust bearing as well. So when we take a look at the losses there, and they're calculated just exactly the same as I would in vibration analysis. The peaks are exactly where they should be. I don't have harmonics of them. We just have the one time. And small peak. So if I see 3 to 5 dB above the noise floor, I know I have a defective bearing. So in this case, when we took a look at it, we found the thrust bearing had the highest load. They were concerned about the others. So I said, hey, what did you do with the alignment? And as it turns out, the thrust bearing was so high because they had left out a shim. So the coupling was bolted together, and it was causing some damage on the thrust bearing. So, but we had the other losses as well. So a total of 11 kilowatts. They removed the bearing, sent it in, split. So we were able to take a look at it, and as I had mentioned, inner race, which was false Brinelling, outer race, which was false Brinelling, and this was the ball signature, the result of the ball signature. 2 of the balls had been dragging in the cage, and then the rest of them should have looked like this, or they should all look like this, nice and shiny. So this and these were the measurements we were seeing for the bearing, and then when they properly aligned the thrust bearing, all that went away. Now there's some other signatures. Oh yeah, so but half of what they were before. This was much higher because you always have some friction. So the total remaining friction was about 2.4 with the new bearings in proper alignment. So yeah, you don't ever fully eliminate it. You just dampen the peaks a little bit. That's where your efficiency is in any case. So still existed a little bit, and that was it. Those peaks are gone. So with that, that should leave us a little bit of time for questions. So Paige, I'm ready.
Perfect. Thank you, Howard, for that great presentation. So just like Howard mentioned, guys, we're going to go ahead and switch it on over for the Q&A session. So if you have any questions for Howard and you haven't already submitted them, go ahead and do so now. Again, just as a reminder, your questions will be asked on the air anonymously, so no need to worry about getting called out. And if we do happen to run out of time here and don't make it to your question, we'll be sure to share those with Howard, and he'll follow up with you after the webinar is completed to make sure that we get you the answers that you're looking for. So Howard, our first question up here that came in while you were presenting, this person is asking, is the tons of COSMWH, which, excuse my pronunciation, is the tons of that a standard?
Is it a standard? Yes, you actually get it from EIA.gov, and it's broken down all the way down to county if you want. So the metric tons of CO2 is a global standard for measurement. That's what we use in any climate related stuff and so on. We use it also, in some of the work I'm doing as chair of standards for wind, solar, and energy storage for American Clean Power. So DOE uses it. We've used it since the 1970s, believe it or not. In the 1990s, definitely used it all the time. So metric tons of CO2, and you can also use some of the other emissions values that are available there. CO2 has a greater value and has been marketed much, much better than the other losses which actually cause more damage than CO2 does. But yeah.
Okay, great.
and EIA.gov, which is a U.S. government website, has values not just for the United States, but for all countries. And most countries have their own as well.
Perfect. Awesome. Thanks, Howard. Okay, so our next question up, this person is asking regarding belt tension, your belt tension example. How did you evaluate energy loss separately from belt and static eccentricity? And then they're asking, won't we obtain only total energy loss?
Yeah. Okay. So that's why I showed the other example later. If you don't have an ESA device like ours, where we can take, each bearing frequency has its own frequency, and on our kilowatt screen, each frequency also shows up there, but it shows up just like vibration as a one-time, but it'll show the actual kilowatt value for that component. So whenever I see a defect, I go immediately to that screen because I'm lazy and I don't want to calculate out the foot-pounds by frequency. The static eccentricity, exact same thing. Static eccentricity is the number of rotor bars or rotor slots, depending on the machine, times the running speed plus and minus 1, 3, and 5 times the line frequency, whether that line frequency be 60 hertz, 50 hertz, or whatever frequency off of a variable frequency drive. So once I have those established, then I can go in and take a look at those peaks in kilowatts, and that gives me the number. And as soon as I have that number in kilowatts and I multiply it by the hours of operation, and then I can take that and multiply that by, I just use 0.707 because that's considered the average. I think EPA uses 0.709, but EIA's is more up to date. That's 0.707. And I'm expecting their next report to show it as slightly lower as well, as we've been decommissioning different types of plants.
Okay, great. Thanks, Howard. All right. These are great questions, guys. Keep them coming in. So the next one up here, so this person says they see a possibility to extend this analysis to non-rotary equipment using power wasted or capacity decrease. What has been your experience calculating emissions for non-rotary equipment? Are there any tips to consider?
Okay, as a matter of fact, absolutely. You can do steam systems. You can do literally anything in the plant that consumes energy. Lighting systems, everything. If you look up U.S. Department of Energy challenge programs, it'll take you to the webpage. I'd give you the exact address, but it changes almost on a monthly basis as they update the website. But all of the work that was done way back when is still there. My dissertation covered way, way, way more than rotating machinery. So yes, everything has an energy number associated with it, whether it be lighting systems to you name it. There's also something to consider as you put in, say, one of the things we found was people were going from fluorescent bulbs to LED and a calculated energy savings, but it wasn't showing up on their bill. Well, the reason why is it turns out the amount of harmonics that an LED system puts back into the system, third harmonic, would often equal the savings. So the next step would be to filter those conditions, and then you get your actual savings. So yes, for static systems, you've got that. For steam systems, steam traps, and condensate return. I'd say when I was at General Motors, that was probably one of our biggest returns. Was returns on investment, was the measurement of condensate return through corrections we'd make in the system. Steam traps are a huge opportunity as well, considering that on average 10% of steam traps fail a year, and so on and so on and so on. So yeah, everything has a measurement, and there are direct calculations for it.
Okay, awesome. Thanks, Howard. All right, so our next question up here, this person is asking if you would mind repeating how you calculate CO2 emissions for equipment to compare for improvement.
Okay. So CO2 emissions, believe it or not, it's a really simple calculation. So if you don't, or you haven't gone to look up the table for your area, and I do recommend reading the instructions first, because as with all government things, they try to make it a little complicated. But 0.707 is a good average value, but neither here nor there. 0.707 is the published annual value for the United States. So I use 0.707 metric tons of CO2 per megawatt hour. So if I'm doing an electrical system, I would take how many ever kilowatts, or if I actually have my kilowatt hours, that's easy. But if I take my kilowatts for that particular measurement, whether I'm looking at an individual item, or I'm looking at the overall, or I'm looking at the improvement in kilowatts, multiply that by the hours of operation per year. I would say if you have a variable load, take the average, multiply it by that. And then that gives you kilowatt hours. Divide kilowatt hours by 1,000, which gives you metric tons. Which gives you megawatt hours. Then multiply that by 0.707 or whichever value you select, and that gives you metric tons of CO2. And remember, metric tons are 2,240 pounds. So it's not English tons, which are 2,000. Okay. I think that should have answered it. If not, I think that might be something I can send in as a short article for CBM.
Perfect. Yeah, we would love that. We would love that, Howard.
Oh, yeah. Examples. I've been trying to get people to do this for ages. I mean, when I was at General Motors, I won 5 People Make Quality Happen awards from the CEO between 2005 and 2009. One year I wasn't there. Based on these programs, because they hit all the way to the CEO. I mean, come on. We've been talking about this for I don't know how many years. How do we reach a C-suite? Show them a number that matters to them. Energy reduction is huge, and right now in the present environment, also relating it to emissions. I mean, when I was at the Energy Resources Center, we were required when we were asking for grants to produce the CO2 emissions reduction as part of that. So when you go up to the board and they have set in their mission that they're going to be, a good global citizen, regardless of your feelings about it, but if your company has made that decision and they need to report it to investors, showing that your maintenance program is having a direct impact, you want to get attention on your maintenance and reliability program, that's a way to do it. And it's not a correlation, it's a direct measurement.
There you go. Very true. All right, Howard. So we've got one more question here, and I know we're a little bit over our time for today, guys. So stick with us if you can for one more question. If not, you'll receive a copy of the recorded version, which will include everything that we've covered here today. But to wrap things up for today, Howard, one last question. So this person is saying that they see a lot of IoT sensor manufacturers claiming energy savings and being environmentally friendly. They say it seems unrealistic to them. Is ESA, in your opinion, the only true way to show the true impact of energy savings of increased reliability?
So in the day after tomorrow at the Vibration Institute, I'm doing two presentations, I've got three presentations going on, but we're doing a paper specifically where I'm relating this to the losses measured directly from, say, vibration analysis. So can you? Yes, I have had an issue with some of them that have been using kind of like rule of thumb and made up numbers. It's a little more complicated when you're doing something other than a direct measurement, but there is a way to do it. So yeah, some of them are there. Now, one thing to remember with IoT devices, and I have an IoT device. What we did, because we have a very strong, because of my background, very strong bend towards savings. A lot of IoT devices actually use more energy than they should, especially if they're cloud-based systems. Now, this is just for storage, let alone the actual processing. Then the U.S. average consumption for per gigabyte on a cloud storage system is 7 kilowatt hours times how many ever hours, right? Per gig. If you're doing it on board a gateway or local PC, it's 0.00004 kilowatt hours. Significant difference. So what we ended up doing is I then changed it so anything we move to the cloud is measured in megabytes. So 2 years worth of data from our system is about 2 megabytes versus moving up gigabytes of data per measurement. So and we keep all that stuff on the local PC, on the gateway PC versus in the cloud, unless you're doing a backup, and then you have to be conscious about it. So yeah, the move from standard applications to cloud applications has had the opposite effect than what we deal with, because I do data centers too. And I tell you what, when you walk into a data center, you're talking about, some sites having, they're not usually measured in a megawatt or two energy consumption. They're measured in hundreds of megawatts at each site. And there are more of them going up every day. So it's just something to pay attention to. But IoT devices in general, all of us old school guys are a little concerned about losing sight of the equipment and relying totally on machine learning and AI, especially those of us who actually do that stuff. And I've been doing what we now call machine learning, data science, and everything since the mid 1990s. So and other things before that. So we know what the accuracy really is. And a recent EPRI study, it found that it was not what people were expecting. I think we're going to hear some presentations on that over this week on this channel, and we'll be talking about it at another event too. So just be aware. It's not the solution to everything. They definitely have uses. IoT devices most definitely have uses. I mean, otherwise I wouldn't have them. And you just have to be aware of what the impacts are and what you lose and what you gain. And that could
Okay.
be a whole other presentation.
I know. We need to come up with a series or something, Howard. I swear.
Well,
There's never enough time.
I just presented at EPRI the week before last, Electric Power Research Institute down in Orlando. And this was the topic we were talking on, and it was the big topic there too. As we reduce workforce, what's the actual balance? And IoT devices don't eliminate the need for expertise; they actually increase the need for expertise. So, certified vibration analysts, ESA people, infrared, ultrasound, all that stuff becomes even more important with IoT devices, not less.
Very well said. All right. Well, Howard, I think that's our time for today. But did you have anything else that you wanted to add here before we wrap things up?
Yeah, two ways of asking further questions if you have it, because this is an area of passion for me. It always has been. Ask on CBM, on any of the Mobius channels. I'm there. I pay attention, especially if something is directed at me. I get a flag saying, "Hey, you've got a question." I'll answer them. And if you don't want to put it out in public, just email me directly at info@motordoc.com or howard@motordoc.com. Either one is easy. And I'll respond.
Perfect. Well, thank you, Howard, so much for the time. Ohio worked for us. No issues.
Yeah. And
So,
now I have to finish the rest of my trip to Niagara Falls. So,
oh my goodness. Well,
it's
safe
only 4 hours.
travels.
Yeah.
There you go.
Okay.
Safe travels. Enjoy. Thank you so much for taking the time with us this week, Howard. As always, it's a pleasure. So thank you so much.
I'm going to listen to the rest. I'm going to listen to the rest of my drive. So
There you go. Perfect. That sounds good. You can
Yep.
have it on your phone and everything. You can now live
Exactly.
stream. So there you go.
Yeah, I don't want to miss the next one.
Right? I know. It's gonna be a good one, guys. All
Yep.
right, Howard. Well, thank you so much. And then here, everybody, just to wrap things up for today, if you haven't heard already, as a thank you for attending WOW 11 this week, we're pleased to provide you with 50% off of your conference pass to the CBM and Reliability Connect live training conferences, either happening in Mexico in just a few weeks or in Australia later this year. You can use code WOW50 on registration for any of the conferences to reserve your seat and take advantage of that discount. The events include certification training opportunities, hands-on workshops, case studies, sometimes a good old presentation from Howard. You never know which one. And then you can visit mobiusconnectconference.com to learn more about the live and in-person events. You can also sign up. We'll include a link to register in the follow-up email after this webinar. And then coming up next, as Howard alluded to, we're not done just yet for the day, guys. We've got a few more. So we've got assistive intelligence, integrate domain enterprise, and technology to improve results, presented by Chris Klosterman, coming up next in just about an hour or so. If you've already signed up, great. I'll see you there. If not, be on the lookout, or you can just jump into the attendee hub and look for the join now link, and you can jump right in. You don't need to take any other steps to register. You can just hop right on in and enjoy the session. That one's bound to be another good one here. Be on the lookout for an email from us containing the on-demand library information. So in the attendee hub and in the email, you'll be able to have a link that'll get you access into the on-demand library, which will contain all of the WOW 11 sessions from the week. That email will also contain your certificate of attendance. So feel free to pop that up on social media, primarily LinkedIn if you'd like. Tag me, tag Howard, tag Mobius Connect, tag everybody. We love to support you guys along in your continuing education journeys, and we love to see those. And then if you guys are interested in engaging in those other platforms that Howard was alluding to, you can jump up to mobiusconnect.com to create your free profile. In doing so, you can engage on the industry's live feed and ongoing forum discussions. You can also direct message other subject matter experts like Howard there. And you can also follow us on all major social media networks at Mobius Connect to stay up to date with the latest community happenings. And then if you guys have any questions whatsoever, whether it be about WOW 11 this week, a suggestion on a future topic, or just any other general questions, you can contact myself and our Mobius Connect team at info@mobiusconnect.com. Thanks again, everybody, for joining us. I hope to see you at another WOW 11 session this week. In the meanwhile, stay safe, and we will see you next time.